Jennifer Donahue, and I'm going to give you some of the initial results from the broadband platform simulations that have been running since about July. So just as a quick agenda, I'm going to just go over what are the planned use of the simulations, and then we'll get to the good stuff, to the review of the initial sets. So why did we run the simulations? If you're here during workshop number 1, we really started to look at what do we have in the empirical data and how can we use that to augment what we currently have and go forward with some of the smaller magnitudes, especially for the hanging walls. We really don't have that in the empirical databases, and so we ran a suite of magnitude 5.5s and 6s so that we can help to constrain the hanging wall effect. We also compared the hanging wall scaling for some of the mid-level, so about the magnitude 6.5 and a magnitude 7 scenario. We wanted to look at the estimate of the scaling on the ground motions for complex ruptures as well as splay faults, and I'll get into that in just a second. So for the hanging wall scenarios, we really wanted to dive into those small magnitude events. So we looked at magnitude 5.5 and magnitude 6. We looked at 5 different dips, going as shallow as 10 and then all the way up to 60. For each one of those, so for the 5.5 and the 6 and all those dips, we looked at 3 different depths. We looked at 2.5, we looked at 7, and we looked at 12. So that's a lot of different scenarios that we were able to look at for the small magnitude. For the mid-level magnitudes, we looked back at a magnitude 6.5, and so we did 5 scenarios for that and looked at 5 different dips, and with a depth of basically a surface rupture, so a depth of 0. We looked at one magnitude 7 scenario as well, and it had a dip of 45 degrees, and it was a surface rupture. And the reason why we did this is that we wanted to look at all 3 of the candidate models that we have, which are the Graves and Petarca, the SDSU, and XM. In 2011 and 2012, Graves and Petarca had run a series of simulations for us for magnitude 7 and 6.5, but we wanted to see how the other models looked in comparison for the magnitude 7. So this was basically a check to see how we were doing. So in all, for the hanging walls, we had 37 scenarios, 32 realizations each. The 3 methods that I already mentioned, so we had 660,480 seismograms. So that was really a lot of fun to try to download from their website and crank through. So Katie and I, that's basically all we've been doing for about the last 3 weeks. So what did it look like? This is just a magnitude 6.5 with a dip of 45 degrees. This is the station map that we used. We used the same station map for the magnitude 6.5, the 6, and the 5.5. So here you see the surface trace at the top of the fault with the dark line at 0, and the surface trace of the fault is given in the dotted line as you're going out. So again, we use the same stations for the magnitude 5.5 and for the 6 as well. One of the items that we try to make sure of is that none of the stations fell on top of the edge of the fault, so this is the best configuration that we could come up with. But for the magnitude 7, we needed something a little bit larger, and also because we were trying to look back at the Graves and Petarca simulations that were run back in 2011 and 2012, we used this type of station map in order to run the magnitude 7s. Okay, so I know that Katie's going to get into this a little bit more in her presentation, but I'm going to just give you a quick overview of complex and splay, just to make sure that everybody understands the definition. So complex is a significant change in the rake or the dip along strike. So what we have is you have one fault coming down, and then it peels off onto another secondary fault that you might have a strike slip is going onto a reverse, or a strike slip onto a normal, but you have a significant change in the rake or the dip. So that's complex. And a splay fault is that if it just continues on. So here you have the fault that's continuing on, and then you have this secondary fault as well that's coming off to the side. So Katie's going to quiz you on that next, so everybody make sure you take notes. Okay, so for the complex and the splay faults, we broke it into 2 items. So first we had a Hosgri that went onto a San Luis Bay, which was a reverse, and we also looked at a Hosgri strike slip onto the Los Osos, which was also reverse. For the splay, we went from the Hosgri to the San Luis Bay, which is a reverse, but again, now the Hosgri is running all the way down, and then you have the secondary fault, which is the San Luis Bay. We have the Hosgary strike slip and the Los Osos reverse, but we also have the Hosgary going to the shoreline. So you have a strike slip going on to a strike slip. Eventually, we will also add in San Simeon and San Gregorio. So at this point now, we're linking up different segments of faults as they're starting to go north. And so you're probably wondering, okay, what's the difference between the complex and the splay? Like, for instance, the Hosgary to the San Luis Bay for the complex and the Hosgary to the San Luis Bay splay. Well, now you don't have that across from, let's see, let me get to it real quick. As you're coming down, so if this is the Hosgary that's green, and this is the pink line that's the San Luis Bay, when you're talking about the splay fault, you're going to continue the Hosgary all the way down, so you're getting a contribution of the full Hosgary and just the contribution of the San Luis Bay, as opposed to the complex, where it's going to run down the green and then it's going to move on to the pink, and you don't have a contribution from this at all because it's not following through. Okay, so we talked about what the difference is between the complex and the splay. There's two different modes that were run for the simulations. We had a fixed hypocenter, and we also had it with random slip, and then a random hypocenter with random slip. We had two model widths. One was thick and one was thin. And I will just tell you now, we're going to have a lot of discussion on this coming up in the next couple days. So one of the modelers would like to make sure that the depth does not go, basically they're looking for a 22-kilometer depth. And so you're adjusting the width to that. And then the other two models aren't as sensitive to that. So we ran both thick and thin models. But again, we're going to have a lot of discussion on this in the next couple days. So for this, we have 14 different scenarios. Again, 32 realizations per scenario, 3 different methods, 116,928 different seismograms. Just to review the faults for everybody, the blue line, that's the San Simeon. Above that is the San Gregorio. We haven't linked that one in yet. The green is the Hosgary. The red is the Los Osos. It's a reverse fault. The pink is the San Luis Bay. It's also a reverse fault. And the light blue line is the shoreline, and it's a strike slip. So we use this, and we can't really use a bunch of squiggles. I know that the geologists love to put squiggles in their faults, but you can't really handle that in the broadband platform. So we straighten them out, and here you have the San Simeon, which is still blue, the Hosgary, which is green, and then we're showing the San Luis Bay here. So this is the splay, this is the splay fault, because as you can see, the Hosgary is continuing down. There. Then we also looked at the complex ruptures, which is just the green is going down. But you'll notice that we wanted to keep all of the stations down here as well so that we can make sure that we're comparing apples to apples when we're looking at both the complex and with the display faulting. At this point, we've run pretty much all of the different scenarios, but we haven't run this yet. So we haven't run the little short Hosgary. We've run all the other scenarios and combined those. Katie's going to be showing those later, but we still need to submit these cases here with the short Hosgary to the broadband platform. And that's all I have. Is there any questions?
One question.
Yes.
Is there any comparison?
Wait, sorry.
I'll ask you later.
We have people connected on the line, so it's important that when we ask a question, we state our name and we use the microphone. Thanks.
Is there any plan to compare your results with what Julian is going to do?
Yes.
And that was Yusuf Vodzorny asking the question.
I was going to say, what exactly is... Oh, for the dynamic. Yes, that is correct. We will be comparing the two. I was going to say, we have a couple different Julians, and I'm like, oh, which Julian? So, yes.
We have only one Julian.
Okay. Yes, we will be comparing those, and then we're going to talk about that a little bit later on Thursday, about how we might be able to bring in some of the dynamic ruptures. Go ahead.
Yeah. Is this on? Yeah.
Yes.
So this is Norm. These weren't results yet. If she said results, and these aren't results yet, right? This is the cases that were run. You'll start to see some results through the next couple days from the simulations. But really, these are the first sets of runs, and we are expecting revisions and feedback from the developers of these methods as to what we're going to do, compare them with dynamic ruptures as well as the GMPE. So that's all that's all going to get pulled together.
Great. Thank you.